Hello guys, and welcome back to my YouTube channel. In this video, we're going to be going over how to rank molecules from most to least acidic. We're going to be going over this question, so ranking these four structures with respect to one another. But before I get into actually going over the example, I'm going to be going over a little bit of the theory. Whenever we look at the acidity of a proton, so here we'd be looking at this proton. Is this proton acidic? Well, we got to argue the acidity of the proton based off of the stability of the conjugate base. So what makes the conjugate base stable? Well, we got to talk about resonance, size, induction, and the orbital that the negative charge will reside on, and how that will affect the stability of our conjugate base, and how the stability of the conjugate base will predict the acidity of the acid. So yeah, let's go back to the basics, and let's start our lecture. If you want to skip right to the example, just skip to the end of this video and I will be going over it. If you want to stick around for the lecture, then let's get into it. So, if we're going to argue acidity with respect to the stability of the conjugate base, well, we need to look at, okay, well, what is the conjugate base? So let's go back to the basics. An acid, so for example, in this reaction, HF, the hydrogen would be the proton that is going to be extracted by the base, where we have the NH2, one of its lone pairs is going to go 2 and attack the hydrogen, 2 out onto the fluorine. So since the NH2 grabbed a proton, it is going to be the base. And since the HF lost a proton to become F minus, that is going to be the acid. So then on the other side of the reaction, the NH3 would be the conjugate acid, because in the reverse direction, to become NH2, it's going to need to lose a proton. And then in the reverse direction, the conjugate base is going to be the F minus, because it's going to attack one of the hydrogens attached to the nitrogen, 2 in, 2 out, to get back to HF. So whenever we want to look at how acidic a molecule is, we must argue the acidity based on the stability of the conjugate base. So what does that mean? Every time we're given a structure, we need to remove that proton. So HF, we must remove the proton and we must look at the conjugate base. And we must ask, is this negative charge stable? And if it is stable, if you increase the stability of the conjugate base, this is going to decrease the pKa of the acid and increase the acidity. So that would mean that if F minus, if we determined, and I'm not saying it is very stable, we're going to go over what determines if a conjugate base is stable or not, but if F minus was very stable, this would mean that the hydrogen on the left-hand side of the reaction would be very acidic. All right, so what makes a conjugate base stable? We're going to argue the stability of the conjugate base based off of resonance, induction, size, and the orbital that the negative charge resides on. So let's dive into resonance. So if you are given these two structures, and I asked, okay, which proton is more acidic? Maybe I haven't told you which proton I wanted you to look at. Which proton is more acidic? Okay, step one, what do you got to do? You got to look at the stability of the conjugate base. So I got to remove that proton. So if that proton is removed by some base that's negatively charged, 2 in, 2 up, what do we get? Well, we're just going to get a negative charge on that carbon that initially had the hydrogen that was removed. So same with this guy. If the base comes in and it's negatively charged, it's going to go 2 in, 2 up. Okay, so now we got a negative charge on a carbon and a negative charge on a carbon. So now I got to ask, okay, well, which conjugate base is more stable? Well, the negative charge is on a carbon atom in both of these structures, so we cannot argue it based off the atom. Now we got to ask other questions. Okay, is there resonance? Is there any inductive forces? Here we can see in structure number 1, we'll label this 1 versus 2. This negative charge can be delocalized via resonance, 2 in, 2 up. We can actually draw a resonance form. So 50% of the time we could think about this, that the carbon doesn't even need to have that negative charge. It says, hey, oxygen, you have it. So the oxygen has it, some of the time, and the carbon has it some of the time. So when we move this negative charge over a greater area via resonance, this is going to increase the stability of the conjugate base. So this conjugate base is increase the stability via resonance. Therefore, I'm going to decrease the pKa and increase the acidity in comparison to structure number 2, because this negative charge cannot be delocalized. So it stays on this carbon atom where it is very unhappy, because carbon is not electronegative. It does not like having a negative charge. It is, quite frankly, electropositive. So when it has a negative charge, it is very unstable and reactive. Therefore, its proton in the acid form is not going to be very acidic, because it doesn't want to leave, because it's going to leave behind a very reactive, unstable structure. So that's resonance. So who's more acidic? Well, compound number 1. Hydrogen would be more acidic, and the reason we just went over would be resonance. So the next thing we're going to cover is induction. And you were asked, okay, which hydrogen is more acidic? Step 1, we always got to look at the conjugate base. So we got to remove that hydrogen. And that carbon that initially had the hydrogen is going to be left with a negative charge. So that carbon now becomes negative. And now we have the same case as last, where we have a negative charge on a carbon atom in both of the structures, in structure 1 and in structure 2. So we ask, okay, well, can either of these carbons delocalize this negative charge through resonance, for example? No, there's no pi bonds near this negative charge, so it can't be delocalized. So then we can ask, okay, well, is there any electronegative atoms near this carbon that holds the negative charge that could inductively help me out, that like to pull electrons towards themselves so they can help stabilize this negative charge via induction? Yes, there's fluorines on compound 1, and there's chlorines on compound 2. So which compound is more electronegative? Hence, which compound pulls electrons with greater strength towards their side, which helps me stabilize the negative charge? Well, the fluorines are more electronegative. Therefore, their pulling force is greater. You can think like tug of rope. It's pulling a greater force, greater amounts of electrons towards themselves. Hence, we could think delocalizing that negative charge via inductive forces. So this conjugate base is more stable. This compound is more acidic. More acidic. So that's if we're looking at induction. The next thing we're going to look at is size. If we think, okay, these are the conjugate bases, right? So this would have came from an OH, and this would have came from an SH. And we were asking, in comparison to structures 1 and 2, which one is more acidic? Which is more acidic? So which hydrogen is more likely to leave, while which conjugate base is more stable? So we have an O- versus an S-. Which atom can better stabilize this negative charge? In the other 2 examples, we had a negative charge on a carbon atom in both of the structures. There was only a negative charge on a carbon atom. So we could ask, okay, around this carbon atom, is there any atoms that can help me out? Well, here we have a negative charge that's residing on 2 different atoms. So we got to compare the atom. So which atom can better stabilize this negative charge? The bigger one, because when a negative charge resides on an atom with a larger atomic radius, there's a greater amount of space. And since electrons hate one another, and there's a larger space that this negative charge can occupy, so there's more space for these electrons, they don't have to run into each other as often. So there's less repulsive forces. That's how you can rationalize this. So the atom with the larger atomic radius, if we're comparing a negative charge on an O versus an S, so 2 atoms in the same column, we'll look at which one is bigger. The bigger one is going to be able to better stabilize that negative charge, so it's going to have a more stable conjugate base to increase the stability. So it's going to decrease the pKa of the acid and increase the acidity of this guy. So this one would be more acidic. We're going to look at orbital. I'm only going to briefly touch on this. So essentially, if you have a negative charge that resides on an atom, that would be sp, versus an atom that would be sp2. Well, if there's a greater percentage of S character, that means you could think of this like if there's a greater % of S character, there's a greater amount of nucleus, where the nucleus would be a positively charged entity. And negative charges, since opposites attract, love the nucleus. So this negative charge that resides on a carbon with a higher % S, this would be 50% S and 50% P. It's going to see a greater amount of S-like things, so a greater amount of nucleus. Therefore, this conjugate base would be much more stable than this conjugate base. So this compound, when it has its proton, would be more acidic than this guy. This proton would be much more acidic than that guy. So now that we've covered a little bit of the theory, we covered resonance, induction, size, and orbital. Now let's do a question. If you're given 4 structures and you're asked, okay, rank the acidity. Well, which proton's acidic? Well, they made it pretty obvious. They drew in that proton. So step 1 is I got to look at the conjugate bases. So remove that proton. So redraw the structure with the proton removed, because you're always arguing based off the stability of the conjugate base. So we really don't care what it looks like in its acidic, in the acid form. Well, we do, but at the same time we don't, because, well, we need to look at the stability of the conjugate base. Okay, so first things first, we can see that these two structures look very similar. There's a C double bond O. So that means we can perform resonance in both of these guys, 2 and 2 up. 2 and 2 up. Whereas in these two structures, there's no resonance available. That means automatically these two guys are going to be more acidic, or have a more acidic proton, than the other two. So let's compare these guys directly. Okay, well, what's different about them? We have a S minus versus an O minus. And they both can, delocalize that negative charge via resonance. So we can't compare the resonance when we're looking at the comparison of these two structures. So we got to compare the atom. And remember, larger atoms can better stabilize that negative charge. Therefore, this conjugate base is going to be the most stable. Therefore, this compound is going to have the most acidic proton. So then, since this structure still has the resonance, though, it's going to be the second most acidic. So this proton is going to be the second most acidic. So now we have to compare these two structures. Well, we have an O minus and we have an N minus. Well, these guys are in the same row. So if we're in the same row, then we need to argue based on electronegativity. So here the O minus is going to have a more stable conjugate base because oxygen is more electronegative. And when they're in the same row, the two atoms with the negative charge, we must argue based on electronegativity. Where electronegative atoms like to have electrons more than atoms that are less electronegative. So if you like having electrons, that means you're going to be more stable. So this guy is going to be more stable than when the nitrogen has a negative charge. So this would be the third most acidic, and this would be the fourth most acidic. That is it. That is all. I hope this video made sense, and I hope it helped you out when it comes to ranking structures based on acidity. We got to look at that conjugate base when we argue based on resonance, induction, size, or the orbital. Yeah, let me know if you have any questions. Leave them down in the comment box down below, and make sure to leave a like, comment, save, and or subscribe to my channel if you like my content, and let me know what topic you want me to cover next. Bye!